equate, like when we leave class today, do you know what an exponential equation looks like? You might not remember. That's our goal, to review that. Do you know when the exponential equation represents growth and decay? Do you know how to graph an exponential function? And then do you know how to tell, like, if a table of data is exponential? So the big thing to remember about exponential functions is they represent repeated multiplication. And we happened to do some things with some fraction exponents last unit, so that kind of helped us, but that exponent just means you're repeating by that base over and over and over again. And so the way that the function or equation is written is f of x, or you might see y, equals a times b to the x. Okay, and that would be what an exponential equation looks like. So let's kind of point out some things that we notice. Where is the x? Yeah, okay. And so the x is in the exponent. So sometimes students will start to get confused when we start talking about like things like this, because that has an exponent, correct? It's not an exponential function though. To be exponential, the x has to be in the exponent, because what that x represents is how many times you're multiplying. If x were 1, you're multiplying by this value once. If x were 2, you're multiplying by it twice, and so on. Now, sometimes you're not going to see a value right here. Okay? Sometimes there's not going to be a number there, and then we're going to write a 1 there. So a in this case is going to represent the y-intercept. When we start talking about modeling this, like tomorrow, I'll click it here. There we go. It's also considered the initial value or starting value. B is our constant multiplier. Sometimes it's called a multiplier rate. For instance, when it's a percentage. Okay, we'll talk about how we change that tomorrow. Okay, so let's talk about, before we tell if data is exponential, how we tell if something's growth, and then just basically what it looks like. If we were graphing an exponential function, and again, we're all dealing with this equation right here, and we plotted some points, and we saw that it went like this, we call that a growth situation. If something is exponential and it's a growth situation, this b value right here, as long as x was a positive exponent, okay, in this form, b would have to be a number greater than 1. And I want you to think about that. Think about what happens if you multiply by a number greater than 1. Doesn't something get bigger? Yes, okay? So this is growth because what we're multiplying by is a number bigger than 1. And just so you know, remember over here what I said, whatever a is, that's the y-intercept. So when we're graphing these things, which we'll do some in a second, you can just do some of them in your head sometimes, or you can make a little table and use your calculator to graph. Okay. Also, do you notice this right here? Remember what it's called? Not yet. We'll go back to it. This is called a horizontal asymptote because it does not cross it. And so exponential functions has a horizontal asymptote at y equals 0. And if I start adding and subtracting things, which I will tomorrow, off the back of that expression, that moves it up and down. All right, let's write that down actually though. Horizontal asymptote y equals 0. Isn't another name for that the x-axis? So make sure when you're sketching graphs today that you make it look like it's approaching but not going across that. Okay, on the flip side, decay, what does this look like? So we are still going to have y-intercept. This looks like it's like reflected over the y-axis. So a decay graph would look like that. This is still your y-intercept. Oops, I flipped that around, didn't I? 0a. Still does not cross the y-axis. What do you think, what kind of number do you think b is, or the multiplier is in this case? Not less than 0, because if it were negative, that would make the values negative. But you're on to something. Less than what? Less than 1. So I'm going to say that we don't want it to be negative, because making it negative would actually change the values to moving them down here. So we're going to say that b is a value between 0 and 1 in order to be a decay situation. This also has a horizontal asymptote of y equals 0, or the x-axis. Okay, last thing before we try some different examples together. Couple things. How do we tell if data is exponential, or basically how do we tell if data or an equation from a graph? So first of all, I already talked about how you figure out a. A is the initial value on the graph. It would be the y-intercept. How do you figure out a multiplier? Well, you got to figure out what the values are multiplied by, right? So if I wanted to tell if data was exponential, what I would be checking is the ratio of y values would be the same. What does the word ratio mean? What operation is that in math? Ratio. Fraction bar, what operation is that? Division, yeah. So we're going to check and see, because if I wanted to see if something's multiplied and I have all of it, I'm going to go backwards and see if it was divided. Okay, so is the ratio of y values would be the same. And that ratio of y values would actually be b. So what I mean by that is, to find b, you can take any y value, I'm going to call it y sub 2, and divide it by the previous y value, y sub 1. Okay. Let's do some examples. I have some equations of functions here. Growth or decay? Decay. All right. Would you circle for me on the graph the y-intercept? Hopefully you circled 5. So 5 represents this value right here. Now we need to figure out the multiplier. Now some of you can just probably look and tell. This is 5. I'm going to go right here. I don't know. It looks to me like that's 2.5, but I'm not positive. Let's go back one. What's this one? How high is that y value? 10, right? So I'm going to just show you what I mean by this. Do you see that this point goes through negative 110, 0, 5? I'm not positive, but this looks like 1 and 2.5. Okay. What are the ratio of y values? And remember, we want to figure out what they're multiplied by going forwards. In other words, how would you get from a 10 to a 5 and a 5 to a 2.5? What are we multiplying by? What's that? One half. Yeah. And if you wanted to, you could take any y value and divide it by the previous y value. If you took 2.5 and divided it by 5, that's 0.5. If you did 5 divided by 10, it's also 0.5. Okay. All right, so we found our multiplier. Our y-intercept was this. Our function is f of x, or y, equals 5 times 0.5 to the x power. All right, so what I want you guys to do is, would you try to do this one? I give you the 0.04 and 1/8. Would you try to write an equation for that? All right, would you take a peek with somebody either next to you? Compare. Okay. All right, so I'm hoping that we started with, and by the way, if you are more comfortable with writing y equals instead of f of x equals, that's okay. Just, you might see it written both ways. I hope we all started this by putting a 4 there. Okay, good. This is growth. Okay, the next point is 1/8, so these are all multiplied by 2. By the way, you might be wondering, why does she put it in a parentheses? It's just an old habit. You can do a multiplication symbol. If it's a fraction, you want to put it in a parentheses so you remind yourself that the whole fraction is raised to the x. But if you have just the dot for the multiplication like we have up there, that's fine. How did we do? Okay? All right. We're not going to do all of these. I don't think I need to do all these. I literally took some of these examples straight out of your Algebra 1 note-taking guide. I didn't even change these two. I didn't even change them. She did this 2 years ago. Some of you, it was 1 year. Okay, now, some of these you can graph by hand. Like you can think, what's the y-intercept here? 1.5. Okay, well, these are going up by 2s. I don't see that, but 1.5 would be right here. And then just start multiplying by, you can't see that. Start multiplying that by 2. Okay, what's 1.5 times 2? You can show me with fingers. Okay, it's 3. So this would go through, then 1, 3. Okay. This is my multiplier of 2. Okay, if I multiplied this by 2 again? Now where is it? 6, right? So then this would go through the point. Oh, are you looking at why I put this here? Because I'm silly. All right. That's at 6. Should be at 3. This is 1, 3. This would be 2, 6. What's 6 multiplied by 2? 12. Okay, so then it would go up to 3, 12. Now, do not try to draw a line through this point. I'm going to cringe if you do that, okay? Because these are exponentials. You need to know it's a curve. So you take your points, you make sure it does not go below the x-axis, and they go up like this. This is growth. So sometimes you can just do that in your head. You don't need to make a little table, okay? I think most of us do not know how to multiply by 0.86 in their head. I don't. So this you would need a calculator for. And I would just make a little table of values. Let's do a few of them. So I'm going to just, right here, I'm going to have an X and a Y. And since I have -1 on here, I'm going to do -1. Let's do 0, 1, 2, and let's do 3. Now, I type in my calculator, 21004 times 0.86, and I raise it to the -1 power. And these are going to be decimals, so I'm going to just truncate to the nearest whole number. So that's what I got. You shouldn't have to put 0 in, because what's anything raised to the 0 power? 1. So this should be, which makes sense. Remember how we said that was our y-intercept? All right, let's raise this to the first. I get 18,063, and let's raise it to the second. 15,534, and then to the third. That'd be a 60. Okay. And then it helps us to know, just be smart about this. Is this growth or decay? Decay, this multiplier is between 0 and 1, and then we're going to just plot some of our points. So when I'm looking at the -124 something, it's going to be way up here. I'm just going to, doesn't have to be exact, okay? 0, 21,004. Well, here's 20,000, here's 21,000. I'm going to just put it right there. 1, 18,063. So I'm going to put that slightly above the 18,000 mark. 2, 15,534. So I'll try to go slightly above where I think 15,000 is. And then 3, 13,360. This is where, now, have these points started to curve a lot yet? They haven't, but you still got to make some curving in your graph, okay? This is not a line, so we make sure this is an exponential curve. If this were to continue, this would, I didn't do such a good job of that. This would continue to level off like this. Okay. I know these are long notes today. We're going to only just do one of these because I'm going to not insult your intelligence. So I'm going to just quick show you. I think you guys can see this one's pretty clear. Aren't these y values multiplied by 2 every time? This is exponential, okay? Like something like this. This is not exponential. I can tell right off the bat. I'll show you why. Start at this end. Take 19.8 and divide by 8.8. 19.8 divided by 8.8. I get 2.25. But then if I did 8.8 divided by 2.2, I don't get 2.25. If these were multiplied, that's what I mean by the ratios should be the same, not exponential. That's exponential. This is not exponential. Sometimes it's hard to tell. Like, let's do this last one. Let's check and see if this one's exponential. Let's start at the end. What's 729 divided by 243? You guys have a calculator on you. What do you get? Is it exactly 3? if you start going through, let's double check that they're all 3. We don't have to write it all down. I'm going to do 243. What's before 243 is the 81. Do I get 3 again? Yep. I check the 81 divided by 27 cents. 3. Okay, I think I found my multiplier. What is it? 3. This is exponential. And if I asked for the equation, the initial value is right here, and you guys told me what the multiplier was. It would be 0.01 times 3 to the x. Okay. What we're practicing today is not all of this stuff.